All right, so now we move on to lesson 7.2, which is absolute value functions, and we're going to start off with dealing with linear functions. In part two, we'll deal with quadratic functions, but for now, we want to stick to linear, build all our fundamentals out, just like we did with reciprocal functions in 7.4, and then we go to quadratics once we kind of have the fundamentals here. So dealing with absolute value functions, we want to compare the following. We're going to deal with the function of f of x just being x, or we could say y equals x, and then its absolute value function, which is g of x or y equals the absolute of x. Now we want to see what happens to these graphs immediately when we plug in points of an original graph and the absolute value graph, or the absolute value function. Let's consider the table of values below. If we know that y is equal to f of x, which is just x, that means that in this situation, all the x values directly equal the y values. It's a one-to-one function. So we look at this and we're like, it's a -3, this is going to be -2, this is -1, this ends up being 0, 1, 2, and 3. Now, to get the values in g and x, or g of x is the absolute value of x, which means that all x values that were negative, positive, or 0 all become positive. So for our g of x, all we're going to do is say if x was -3, now it's positive. If the x is -2, then we get a positive output. If we have -1, it's a positive output. And then for all the other ones, it stays the same because they're already positive. All right, now let's graph these out. In the first graph, we're going to write our y equals x, or f of x equals x. I'm going to plot all these points out. So at -3, it was -3, which puts us here. At -2, it was -2. At -1, it was -1. We had 0, 0, which is right in the origin. We have our 1 and 1. We have 2 and 2, and 3 and 3. And once we've established the pattern and we've plotted these points, what you want to do is draw a line through them, put arrows on the end indicating that it goes through these, and then if the label wasn't there, like this label here, the y equals x, we could put that somewhere at the top right or the top left, either, or bottom left, I should say. Either one, that would be totally fine. So there's our first graph. Now our second graph, we're going to go to -3 and +3. And I'm going to just show this in a different color here. So -3 and +3 puts us here. -2 and +2 puts us here. -1 and +1 is here. 0, 0 is here. 1 and 1 is here. 2 and 2 is here. And 3 and 3 is here. Now we're going to draw out the shape here. So we're going to connect it here. We're going to connect it through here. We want to make sure that arrows go on the end of both sides. And then again, if the graph wasn't labeled like it is below here, we'd want to make sure that we label it. Now, here's the number one thing that I want us to pull our attention to, because we're going to define it on our next page, or define it very shortly here. It deals with what happens when we're dealing with the absolute value functions. If the original looks like this as a linear graph, in order to get the absolute, what we did is we said all things that had negative outputs became positive outputs. And so in this situation, if we had all these negative outputs here, they flipped and became positive outputs. The other thing we want to mention here is on the origin, which is here, and on the origin, which is here, this is our 0, 0. I want us to indicate the following. This is actually the invariant point. And I want you thinking about it like this. If this is the invariant point, the reason it's the invariant point is because what is the absolute of 0? It's just 0. So this point, regardless if it's the blue graph or the red graph, stays exactly the same. Now, you can make an argument that the stuff on the right here is potentially an invariant point because it was positive outputs that stayed positive outputs. But the main invariant point, or what we can even call the inflection point, is this 0, 0. But for now, I'm going to make sure that we write this below here. So invariant point at 0, 0. And we'll just make sure we draw arrows to both, indicating that there was an invariant point that existed at both of these here. Okay, perfect. So now we kind of have a rough idea of what happens when we take these linears and we make them absolute. All negative outputs became positive. Now, what we want to consider is which parts of the graph are the same, which parts are different, what type of transformations can be done to create an identical graph, or what type of transformations can be done in order to compare these two. Well, if I look at these here, what part of the graphs are the same and which are different? All the negative x's, and let's actually start off with the same. All of the positive x's x values have the have the same y value. And then what's different? All the negative x values have different y values. Perfect. And then I'm just going to add a little dash in between here because I like to keep those things separate there. So if we look at our left-hand side of the graph, we see that these ones are all the negative values here. These ones include different values of outputs. On the right-hand side, it looks the exact same. And then at 0, 0, it also looks the same. What type of transformations can be done to create an identical graph? In this situation, the transformations that can be done are we take all of our negative values and we make them the absolute values of this, but we're going to just leave it at this. Is there any invariant points on the graph? Points that stay the same in the reflection? Again, we could make an argument that all of this stuff here on the right-hand side stayed the exact same. So realistically, if you listed these in invariant points, it wouldn't really necessarily be wrong. Maybe we make a note about that, but the major one we want to make a note about is the x-intercept. The x-intercept is the main invariant point. So let's just write that in here. The main invariant point is the x-intercept. And hopefully we have enough space here. Yep, perfect, which is at 0, 0, or the origin. The other invariant points, again, we could list them off as that stuff onto the right, but we want to mainly consider the x-intercepts as our invariant points. From the graph, explain the absolute value function is a function, or explain why it's a function. Very, very simple. We scroll up here. I want you thinking about it like this. If I do a green line test, or if I do the vertical line test, which I'll just do in the laser pointer here, any single line that I could draw on this absolute value in terms of a vertical line, it only crosses one time for every vertical line I draw. And from Math 10C, we knew that if we could draw a vertical line or use the vertical line test, and it only crossed one time on that graph for every vertical line you drew, we knew it was a function right away because it's a one-to-one relationship. There was only one x for every one y. So let's make sure we fill that down here. From this, how do we know? From the vertical line test. And then just to get more specific, we say it is a one-to-one relationship. AKA, there is only one x value for every y value. Perfect. Okay. Describe the shape of g of x. Well, it's a v shape. So anytime we have a linear line, we're going to expect to see this v shape, or that it will have some sort of v-shaped overall appearance. If you could sketch the graph of g of x using two linear functions, what would they be? And then state the domain and range of each of the functions. Okay, well, for this one here, what we want to think about is the following. For our overall transformations, if we know that it forms this V shape, so we scroll back up here, we look at our graph in the red, and we're like, okay, we want to form two different lines or two different functions. The first function is just going to be the original y equals x, or f of x equals x. That when it was equal to x, it gave us this component that was going up in the positive nature. If we then see the slope as being negative, the only thing we're going to do is throw a negative in front of it. And together, this is going to make up a piecewise function where we can say that if we want to form a g of x sketch, g of x is actually composed of two different functions. And here's how we write it. We're going to write the first one as x, where as long as x was greater than or equal to 0, it was equal to this positive x. It was the negative sloping graph when x was less than 0. And how do we know to put the equals on this one? Whatever corresponds with the original graph, in this situation, the x was the corresponding with the original graph of f of x, that one gets the equals. Now, what are the domain and ranges of the functions here? Well, of the first one, so let's just write it as, and I'm going to write it as for f of x like this. F of x had a domain where x was just an element of the reals. It went to positive infinity, negative infinity in both directions. The range of that function was Same thing. Why? Where y is an element of the reals. Because there was no restriction. It went up and down to infinity. And if we saw it, we scroll back up here, it goes up to positive infinity, down to negative infinity. Same thing, left and right to positive and negative infinity. So we're good. With g of x, this one changed the range in particular, although the domain is still the same, where we say, hey, we have an x such that x is an element of the reals. The thing that did change with the range was that now we can't have anything that is less than 0. So it's y, where y is greater than or equal to 0, and as long as it was greater than or equal to 0, there was arrows on the end and it extended both directions. And just to emphasize that, let's just make sure we scroll up and make sure that there's arrows on the end of our graphs, which there is, meaning that we don't know the endpoints. And if we did know the endpoints, then they would have a fixed interval. But for this one, we're going to put arrows on the end representing we don't know where these things end. They just continue on and on. Okay, so we have our two different domains and ranges, and we have our piecewise function to describe the overall graph. All right, let's scroll over here. Now, let's introduce some terminology. Again, the absolute value of a function is simply just saying we take the absolute of any single x that we put in, or the absolute of the function itself, and that's going to give us some sort of output that is a reflection of that. A piecewise function is where we put two parts or two different functions together that describe an overall absolute value function. And so again, this will appear on your formula sheet. We look at this and we're like, if it composes two or more separate pieces with their own specific domain and range for the overall function, then on our formula sheet, the generic form is just that if we have the absolute of some basic x, we can separate it into those two different components. But again, it depends on the problem given. And then lastly, we know our invariant points or do not change. And typically, these points are going to be described as the x values. Now, again, we can expand this definition a little bit if we really wanted to, because there are other points that don't change in some of these functions. But mainly, we want to say that the invariant points occur at the x-intercepts. These are mainly where they occur. And again, we could expand that if we wanted to, and we could see, and in this next example, we may see an example where we have a situation where it includes just more than the x-intercepts, but for now, we mainly want to say they occur there. Okay, let's consider the following. We're going to take a linear function and we're going to determine what the absolute value function looks like based on its form. So in this situation, we have y equals the absolute of f of x plus 2. Now, what I would always recommend doing right here is we want to write out, if they talk about the x and y intercepts, we know we can solve this based on just the original graph of this. I'm going to look at this and be like, well, if I want to determine the x and y intercepts, I highly recommend going back to the original, and which I'll write here down below. The original function without an absolute would be just f of x plus 2. And if it was f of x plus 2, then we have this situation where we see this as, okay, to get a y-intercept, we set the x value to 0 and we solve. So for this one, we could say, like, I guess number 1, y is equal to 2. Because if x equals 0, then it wipes out the 5x, and we're just left with this. As a point, this is going to be 0 and 2. So we have our y-intercept, and then of the x-intercept, which I'll go for part 2 here, what we're going to do, and I'm just going to make that a touch bit neater there, as best as possible. I know with this type of pen, it's a little tough. We're going to set our y value to equal to 0 and write it as 5x plus 2. When we subtract 2 to the other side, it equals negative 2 is 5x. X is equal to negative 2 over 5. And as a point, we would say that our x-intercept is going to be negative 2 over 5 and 0. Or you could write this as a decimal if you really wanted to, but 2 over 5 is totally fine for us. In this situation, it would be 0.4. So I guess maybe let's just write it in there just so we have it. 0.4 and 0. Okay, let's graph this down below. So again, what they're going to get us to do is sketch out, if there was no absolute value here, we can just sketch out the original graph of y equals f of x plus 2. We know from here that our slope is equal to 5. Our y-intercept is 2. So let's plot that out first and foremost. Y-intercept of 2 goes here. And what I'm going to actually do here is just, because I know we're going to plot our absolute right over top of this, maybe in the first graph, I draw it in blue. So here's our y-intercept. Our x-intercept was 0.4 or 2 over 5, and it was negative 2 over 5. So it's going to put me somewhere about here. And then I can use my slope to figure out the rest of the points here. I'm going to go down by 5 over by 1. So in this situation, and this should be, yes, our positive slope. So we're going to go down 5 or up 5, doesn't really matter. So we go 1, 2, 3, 4, 5 over 1. That puts me here. I can go up 5, 1, 2, 3, 4, 5 over 1, which puts me up here. Now I'm just going to draw a line that connects through these. So I'm going to draw it as neat as possible. I know sometimes it's pretty tough. We're going to put our arrows on the end. And then I'm going to indicate that this is the original function of y equals f of x plus 2. Okay, now to draw the absolute, remember, we have our one invariant point, which always occurs at the x-intercept, because if we take the absolute of 0 for anything, the absolute of 0 is just going to be 0 itself, so it keeps us here. But now we want to look at this and be like, well, for the other points, what we want to do is maybe sketch out the overall absolute. If I take the absolutes, remember, any y that's already positive or any output that's already positive is just going to stay positive as an absolute. So we don't need to worry about flipping those. It's all the stuff down here that was negative here. If I take the absolute of this negative, it's going to lift it up. So what I'm going to do is I'm going to take the absolute and write, well, if it was down at -1 and -3, now it's going to be up to +1, or -1 and +3, I should say. So it flips that point. Let's see if we can get another point from here. So 1, 2, 3, 4, 5, and over 1. So actually right at the bottom, there's another point. If I flip this one, this is at -2 and 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So -2 and 8, which then is going to put me at -2 and +8. Now what I can do is I'm going to put a dotted line representing the absolute value function. And I'm going to make sure I put arrows on the end. We know that it would overlap this original blue graph as such, like this. And maybe I'm just going to directly overlap it because I don't want there to be any sort of gap here. There we go, arrow here. And then we're going to write this as our red graph is where we have y is equal to the absolute of 5x plus 2. Excellent. There we go. Okay, so our absolute is the one in red. Now what we want to do is, based on this, we're going to state the domain and range of this absolute value function, the one that's represented in red here. The invariant point, if we wanted to list it out here just so that we have it in a coordinate, it was equal to the -5/2 and then 0 like this. And then, hold up a minute, let me make sure I got this all good here. So this is -2/5. Sorry, I knew I was flipping something here. So this is -2/5. There we go. Okay, so there's our invariant point. That's the one that stayed the same. State the domain and range. Well, if you look at this graph, if it extends to the left to infinity to the right infinity, we know that our domain for this function is going to be that XER. And realistically, in this unit, you can just anticipate that that's not really going to change unless they give you a graph, or unless you're given a graph that has like truncated endpoints, meaning like there's not arrows on the end. We're always going to say our domain is XER. For the range, we just need to be greater than 0 because our lowest possible y value exists right on the x-axis or where there's the x-intercept. So to write this, we're going to write it as range, where this is y such that y is greater than or equal to 0, because it can definitely be at the x-intercept, but then it must be all real numbers that are above 0. Awesome. Now, express this as a piecewise function. Okay, well, to express this as a piecewise, we go y is equal to the absolute value of 5x plus 2. So we write out the absolute. We say this is equal to, here's where you put your big curly bracket. We're going to write out the original function, or the one that if we took away the absolute values, it would be this one, 5x plus 2. This was the positive sloping component. Now, when did this occur on our graph? Where was the positive sloping graph where the blue and the red overlap? It was to the right of the -2/5, and because it's equal to where the original graph is, we also can say x is greater than or equal to the -5/2. It's equal to because it was composed on the original graph as well. For the other one, what we're going to do is, if we want the negative sloping version, we just take all of what was the function, put it in brackets, and write a negative on the outside, which then makes this a negative slope, and this occurred at all the points that were less than 5/2, or where it was to the left of this x-intercept. And there's our overall absolute function as a piecewise function. So we can think about absolute values as two linear functions coming together to describe one overall shape. Now, when we get to quadratics, we're going to see that our piecewise might include 3 different components, but for this situation, we can limit it down to, we only have our 2 lines, one positive slope, one negative slope, where the positive sloping line is contained here, the negative sloping line is contained here, and together they add up to make the absolute graph. All right, now let's scroll over to our next page here. Sketch a graph of the following and then write the function in piecewise. Okay, right away, I always want you to write off to the side. As soon as they give you the absolute, just write that you have the function, and you can just, again, write it as y is equal to negative 4x plus 4. This would be, if you stripped away the absolute values, this would be the graph they want you to make. We're going to sketch this one out in blue, and then we're going to sketch our absolute based on that. Now, a couple key components here. The key components I want you to list out are that our negative 4 is equal to the slope, because in mx plus b, it's your slope. Your 4 is your y-intercept. And with these two components, we can actually figure out what this graph looks like in blue, the original. If the y-intercept is 4, that means I'm here. My slope being negative 4, I go down by 4 units over 1, down by 4 units over 1. I go up by 4 units over 1. I continue the pattern down by 4 units over 1, and I end up getting that the one in blue here should represent this original graph. So I'm just going to connect the points. I'm going to make sure I put my arrows on the end again because we don't know where this graph stops. Now what we can do is we can put a solid dot right here at our invariant point. Our invariant point seems to be at 1 and 0. So we're going to write 1 and 0. And then from here, we're going to now flip these other points. If they were negative outputs or negative y values, now they're going to become positive y values. Let's sketch this here. So I'm going to go up above here and be like, if it was at 2 and negative 4, now it's going to be at 2 and positive 4. And then if it was at 3 and negative 8, it's now going to be at 3 and positive 8. And here's the number one thing I want you to notice. Just like in our first unit of quadratic functions, we see that there's symmetry going on. We can now sketch our absolute value function as it overlaps the blue, or it overlaps the original where all the y values are positive, but then it now goes on this other side here. By symmetry, we put arrows on the end like this, and we say that there's this kind of like symmetry across this x-intercept where now all our y values are going to be positive for this situation, and our original graph in blue is just that linear line that was defined by the original linear function. Now, I want to make sure I label this, right? So I'm going to go down here and be like, this is where y is equal to the negative 4x plus 4. For the red graph, I'm going to write this as the reciprocal, or not the reciprocal, not to confuse it with 7.4. This is the absolute value function of negative 4x plus 4. Absolute, done. There we go. I think it's important just to label that and label your one x-intercept or your invariant point, because when you don't label these, if it's all in pencil and you have no way of differentiating these, it can be a little tough. Now, again, you could make an argument logically that these are all considered to be invariant points, all the ones on the left here, because they don't change whether they're the original or the new, but our main invariant point, again, is going to be our x-intercept. Okay, now let's go to our piecewise function. So we're going to say, therefore, our piecewise function is defined in the following way. Y is equal to the absolute of negative 4x plus 4, where this absolute value function can be defined. And I'm just going to move this down actually a tad because I like to center that function. So I'm going to write it like this. And then I'm going to write my bracket going down like this. Perfect. Here's the two components. The first component would be the original graph. This is the original negative sloping line. Where does this blue graph occur? It occurs to the left of the x-intercept, where x is less than or equal to the positive 1. And again, we can put the equals there because that's where the red and the blue overlap, or the original and the absolute. Now, the absolute of negative 4, not the absolute, sorry, the negative variant, or the negative sloping piece of this, which the negative sloping piece is where it's negative on the outside, negative 4x plus 4. We take that original function without absolute values and we put a negative on the outside of it all. This occurred when x was greater than 1. We get this new component where if I'm to the right of the x-intercept, it's all of this absolute part that is now defining the positive sloping line. And again, how is it positive sloping? Because a negative times a negative would end up giving us a positive. And so if you end up, like, let's say you do this, I recommend writing it out like this, but let's say right below this, you ended up writing it like the following. This became positive 4x and then minus 4, where x is greater than 1. If you wrote that in there like that, I would be totally fine with that. In fact, you're telling me exactly what we need to know, where if I was to sketch this out, my absolute value is defined by this line here, which is defined by this. So if you want to distribute the negative in, great. If you don't distribute the negative in, totally fine. Just know that either way is correct here. Okay, and then just to avoid it from like overlapping on the graph too much, let's just take this and move it over. For your notes, you don't really have to do this, but for the neatness of this, I'll do that. Now, do we need the domain and range? It doesn't look like it. I mean, we could state that if we really wanted to, just for pure curiosity. If we state our domain and range, well, again, the domain is kind of standard. It's where XER because it extends left and right to infinity. In terms of the range, we're going to say that our y such that y is greater than or equal to 0. As long as it's greater than or equal to 0, aka it's above the x-intercept, we say that it can be any real number. Perfect. All right, let's go down to example 2. Very, very similar. What we're going to do is we're going to figure out if I knew what the original was, or aka the thing without the absolute value bars, it would be 5 minus 2x. Therefore, let's identify the components. Here's our y-intercept, or the y-int. We also have our slope, which is defined by the -2. Now, this is enough information to plot out the original graph in blue. If I go to +5, that puts me right here. There we go. If I do a slope of -2, it's down 2 over 1, down 2 over 1, down 2 over 1. And we just continue this pattern as long as we need to, such that we have a bunch of points. I can go up 2 over 1, which puts me here. And then again, we're just going to draw our connecting line through all of it with arrows on the end. Okay, now we're going to take our invariant point, aka our x-intercept, put a dot here. The x-intercept, well, if I actually wanted to solve this algebraically, we could easily do that off to the side here. The x-intercept occurs where it's 0 is equal to 5 minus 2x. I could add the 2 across, giving me 2x is equal to 5. My x-intercept would be equal to 5 over 2, or the equivalent of 2.5. So what I'm going to do is I'm going to write this as an ordered pair of 5 over 2 and 0. There we go. And then we can just indicate that over on our graph here, that this is 5 over 2 and 0 for that black point right there. Now, what we're going to do is we're just going to flip all these points. And then again, by symmetry, we actually know where all of them belong. If it was a negative, now it's a positive. If it's a negative, now it's a positive. And then you're going to notice that as we look at it from the left-hand side, which is the original function, to the right-hand side, it keeps this symmetry, which about the linear lines is really nice. So let's put our dotted line representing the absolute value. Let's put our dotted line representing the absolute value, like so. We're going to make sure we provide our labels on the graph. So down here, I'm going to write y is equal to 5 minus 2x, which is the original function without the absolute. The absolute value graph, we're going to write this as y is equal to the absolute of 5 minus 2x. Really important to put your labels. We have our invariant points, fantastic. Now we're just going to make sure we write this as a piecewise, and then also on top of writing it as a piecewise, maybe we state the domain and range, which I know is a bit of a step up from here, but why not? So we write y is equal to the absolute of 5 minus 2x, which can be defined by the following two linear components. The first linear component was the original, 5 minus 2x, which this negative sloping line, or the negative blue line, occurred to the left of the x-intercept, or this part here occurs to the left of the x-intercept, which means that we need to write this as equal to, or sorry, not equals to, but x is less than or equal to 5 over 2. Now, again, why does it have that equals in it? Because if it overlaps the original function, we can say it's equal to. If it doesn't overlap the original function, and now it's the negative version of this same thing, negative 5 minus 2x, where x is strictly greater than 5 over 2, this is that new component where it's the reciprocal of that original graph, or it takes all the negative values, makes them positive, and we form this V shape. But this part on the right is not overlapping the original graph. Thus, we're going to make sure that only the original function includes that x-intercept. This new component here that it wouldn't be included with the original function, we're going to strictly have just greater than at that point. And then again, if you want to write this below where you actually expand that negative in and you write it with the negative in there, that's good. Otherwise, I would just stop here and just keep it at this, because I could distribute the negative in and get that new function. But I mean, this tells me exactly everything I need to know from here. All right, domain and range. Domain, it's going to sound very plain. Domain is just XER. So x such that x is an element of the real numbers. For my range, it's going to be greater than or equal to the x-axis, because we know as long as it's greater than or equal to 0, we're going to end up having it where it can be any real number, because in the absolute value functions like this, all absolutes are essentially making all the y values positive in these linear cases. So we want to write it as this is greater than or equal to 0, where y is an element of the reals. Awesome. Okay, perfect. Now, what we're going to do is we're going to scroll over to example 3, which says, what if we want to consider transformations, or what if we want to go back to our previous unit of quadratic functions and then consider it and see what overlaps there are? Well, if we were to ever sketch the original graph of y equals the absolute of x, this is what we consider our original graph. And I shouldn't cancel that out. This is our original graph. So if you really wanted to, right next to this, I just want you to star this and be like, if we wanted to think about this in a logical way, this is the original graph, or the non-transformed graph. In quadratic functions, we always called it x squared. In this situation, it's the absolute of x. Now, what is happening here? We have a few different things going on that we recognize from quadratic functions. Our a value, or the vertical stretch factor, is always written first. So we write it as a here. We have our p on the inside, and then we have our q on the outside. So let me just make sure I point to all these values here. The a value is the vertical stretch, the p value is the horizontal translation, q value is the vertical translation. This is no different. Now, on the original graph of y equals the absolute of x, it was all the following key points. If x was negative 2, then we had positive 2. And we want to consider it a one-to-one relationship, right? So for all of these, it's a one-to-one. This is negative 1, which meant it was positive 1. On the absolute original, let's say we had, I want to say negative 1, or sorry, 0 and 0, because 0 and 0, if it's centered at 0, 0, which is the origin, we're good. We're then going to write it as x is positive 1. The absolute of 1 was 1. If we write it as 2, the absolute value of 2 is 2. And therefore, these are some original key points that we want to consider. Now, in plugging them in, let's just describe what's happening with each of these as they apply the transformations one at a time. First and foremost, we're going to do a vertical stretch factor of a half. So for every y value, we're going to take it and go 1/2. So if x was negative 2 absolute is equal to 2. 2 divided by 2 equals 1. So we end up getting a y value equal to 1 for the first one. And maybe I'll actually just put in 1 here, like this. So, and because we want to write them as points, actually, sorry, my bad, we should write it as if x is negative 2, the y value is 1. Okay, which makes sense because we're taking the y values and dividing them by 2. Once we know that we're just taking the y values and dividing them by 2, this makes it really easy because it's negative 1, and 1 divided by 2 is 1/2. We then go to our next one. If we take 0 and we divide it by a half, this is still just 0. aka this is our invariant point, maybe an interesting thing to highlight here. We then go to our next one, which is 1. We take 1 divided by 2 is 1/2. We take 2, which is our x. We take 2 divided by 2, which is equal to 1. And then if we wanted to describe this using mapping, well, for every x value we get, we take the y value and divide it by 2. So going back to quadratic functions, mapping notation is the general terminology, or the general structure of what happens to each of the points. Okay, now let's not only do the vertical stretch, but let's also do the transformation. If this is a negative on the inside, this is very important to note. If this is a negative, it actually means we go right. Perfect. I'm just going to annotate that in there because just like quadratic functions, we said that if there's bracketed terms like this and it's x minus 4, it actually means we're going to go positive 4. And by absolute values, that should make sense. The absolute value of negative 4 is positive 4. Okay, so what we're going to do is we're going to take the vertical point, which in this situation is, or sorry, the horizontal point, and we go, well, for every key point that we measured here, what's happening with the y's, they're being divided by 2. For the x's, they're adding 4. So negative 2 plus 4 is positive 2. The y value, 2.5, is going to be equal to 1. There we go. So our new point is at 1. There we go. For this next one, x value being negative 1, we add 4 gives us positive 3. Our y value divided by 2 is 1/2. Then we take this and we go 0, 0. 0 plus 4 is positive 4. 0 divided by a half is just still 0. So now our invariant point has shifted over 4 units. If I take 1 and I add 4, this is going to give me 5. If I take the y value and I split it in half, that's 1/2. If I take the x value, add 4, this gives me 6. If I take the y value and divide by 2, it's 6 and 1. And our general form is the following. X is going to add 4 units by the inside brackets, and then the y values are going to be divided by 2. Okay, last table is we're now going to have a vertical shift or a vertical transformation or vertical translation. We go up in the y values by 2 for each of these. So what I'm going to do is I'm just going to take all of the exact same points because we know the x values would be the exact same, but the y values, we're just going to plus 2 onto each of these. So I'm going to go where x is 2, we add 2, that gives us 2 and 3. Where x is equal to 3, we take 1/2 and add 2. This ends up giving us, well, if we add 2 of these, which is the same as 4 over 2, 4 over 2 plus 1/2 is 5 over 2. There we go, or 2.5. If we take the same x value, because that won't change in these transformations, and then we add 2 to 0, that gives us 4 and 2. If we take 5 and we add the 2, this again gives us 5 over 2, which is that nice symmetry. If we take 6 and we add 2, this is going to end up giving us 3. And then if we describe this using the mapping notation, well, x was still adding 4, the y values were still divided by 2, but now instead of just dividing by 2, we add a 2 because there's a vertical translation. All right, what are the coordinates of the vertex once we do this, all this mapping notation here? Well, the coordinates of the vertex are given by 4 and 2. These are the coordinates of the vertex right here. So I'm going to make sure I just star this and be like, this is where our vertex belongs. Perfect, and I'll star it. There we go, awesome. So down below here, what we can consider our P and our Q of this unit is, and I'll arrow over because this is more formal, it's going to be at 4 for x, 2 for y. What is the slope of each line segment that composes each of the functions? What I would do is I think it's best that we draw it out here, and then we can figure that out. So, I mean, there's a really, really fast way to know this, and it's from the function, but let's just sketch it out, and then we can confirm it. So if my vertex is at 4 and 2, that means I'm going to be here. I'm then going to put in all these other points here on the very right-hand column here. So we have 2 and 3, which puts us to here. We have 6 and 3, which puts us to 1, 2, 3, 4, 5, 6, and 3, which is here. We have 5 and 2.5, which puts us to here. We have 4 and 2.5, which puts us to here, or sorry, 3 and 2.5, which puts us here. And then do we have any other points that we can put? It doesn't look like from this graph here. So what I'm going to do here is I'm just going to draw a straight line through these ones as best as possible. That might be a little bit off. Let's see if we can do just a touch better. There we go. And then I'm going to do the same thing on this side. Straight line through these arrows on the end representing that this continues on. And we have this here. Now, what is the slope of each of these? To get the slope of each of these, we can actually just take the rise over run between any 2 points here. And so maybe I just do that as a demonstration here. Let's say that this point here, which is our vertex point, which was 4 and 2. So let's make sure we indicate that in here, 4 and 2. And these points here on the outsides were going to be at 2 and 3. And this one was at 6 and 3. Then to get the rise over run or the slope, we just go m value, which is the slope, is the difference between any of these 2 points. On the left-hand side, it's a negative sloping line. We have to go down by 1 unit, over by 2 units. This means that the slope is equal to negative 1/2 for this section here. So I'll just arrow to there. And I want to make sure that line is just a touch neater here. There we go. And then for our other segment here, we get a slope where m is equal to, whoops, there we go, m is equal to go from point to point, for our right hand positive sloping, we go up by 1 and over by 2. So this gives us positive 1/2. And so now we have a positive slope and we have a negative slope. And that should make sense because with any absolute value, it's a composition of a positive and negative sloping line, especially on the linear ones. When we get to quadratics, we'll see it's a little different, but for the most part, this is what we get. And so now the slope of each line, we take this piece here and we're going to write it as maybe we do describe it in terms of like the piecewise function of this here. So if I take the 1/2, and then this was the x minus 4, and then it was plus 2. If I take this, well, the slope of this line is equal to 1/2. If I take the negative variant of this, or the negative version of all of the absolute value function, this gives me a slope of negative 1/2. Now, how do you know the slope? It's actually just the a value. Do you see how we had 1/2 here? The vertical stretch factor, this one typically indicates your slope. However, it might be a good idea to go on your graph and just confirm that, but your A value is a very strong indicator. The domain and range on this graph, well, if we look at it, if it extends to the left and right infinity, no surprise again, we say our domain is where we have x such that x is an element of the real numbers. For the range, we're going to consider this where it is y such that y is greater than or equal to our lowest point here. Instead of it being on the x-intercepts, because of transformations, it's actually shifted up to positive 2. So now we want to write this as 2, where y is an element of the reals. Perfect. So this is the first time we're seeing our invariant point above the x-axis, and that's why we can say it is our x-intercepts, but it's not always, because we can describe invariant points as, depending on the transformations, it can be raised up a little bit. And in this situation, it would be the same right here. Okay, write a piecewise function to describe the graph. Here's our piecewise. We're going to write it as y is equal to 1/2 the x minus 4 plus 2, which can be described using the following linear lines. The first linear line here is going to be where we had our original function, where it was x minus 4 and then plus 2, like this. And then we have this where this was for all x values that were to the right of the x value being 4. So we're going to write this as x being greater than or equal to 4. And this would be symbolic of the original. The other line segment is where it's going to be negative, and we throw a negative in front of this as negative 1/2 of x minus 4 and then plus 2, where x is less than 4. Perfect, because all of the negative sloping things happened to the left-hand side here. Awesome. Okay, let's flip our page here. We're going to look at some transformations, and just again, I've been mentioning this terminology in that past example, but we want to consider the following. Just like we did in our Unit 1 past factoring when we got to quadratic functions, the A value is the vertical stretch, the P value is the translation in the horizontal direction, the Q is the vertical translation. So very important. I would just highlight this in your notes. Vertical stretch factor and the vertical and horizontal transformations. If A is greater than 1, it looks taller, so it's going to be more straight up. We know that the slope of the graph, which is this A value, if you really want to consider that, the slope of this, when the vertical stretch factor is large, it looks steeper. If the vertical stretch factor is something like between 0 and 1, it looks more flat, and so we should be expecting that 1/2 is going to look a lot flatter than something with something like a 2 for an A value. Now, when we look at these, when we look at any sort of absolute value function, if it's an absolute of x, well, that means that there's going to be some sort of positive sloping original graph. And to get the absolute value of that, what we would need to do is take any negatives and then make them positive up here. If the negative exists outside the absolute, you actually see that there's a vertical reflection about the x-axis, which again is no surprise to us. So we haven't seen in the notes thus far an example where it's below the x-axis like this, where our absolute was this, but that occurs if there's a negative on the outside of the absolute, because again, we consider this to be a vertical reflection about the x-axis, which that might be something to really highlight here and pull away. The last thing I want you to highlight here is the following, or the second last thing I should say, is that mapping notation for any point that you might put in from the original, we always add or subtract the p-value depending on what it is. We take the vertical stretch factor of A and we multiply it to y's, and then we add or subtract the q value depending if it's positive or negative. The value also gives the absolute value of the slopes of the two linear functions. So if we take this absolute value function, we can actually get the slopes quite easily out of this, and it allows us to kind of generalize the overall piecewise of the graph. Now, example 3, let's see if we can sketch this out using transformations here. So what I would recommend doing is maybe doing some mapping notation on this thing, and then what you could even do is describe the original graph or draw the original graph if that helps. So a couple major things we want to pull out of this here. First of all, when we describe the mapping notation of xy being transformed into the new points here, the new points occur with the following. If it was plus 2 in the brackets, now it's every point of x is going to be subtracted by 2. So that's what happens to the x's. In terms of the y's, there's a vertical stretch factor by 3, and then there's a vertical translation of -4 units downwards. So every single point is going to go through this mapping notation here. Now, our vertex point occurs just like it did in quadratic functions at the p and the q. So let's write that in here as well. Our p and our q are located at where x is -2, y is -4, or the p and q are -2 and 4. Okay, for the sake of this one, what I kind of want to do is I want to just draw out the original. The original would be y equals the absolute of x. The y equals absolute of x is written like this. 0, 0 is the origin, 1 and 1, 2 and 2, 3 and 3. We then can go all the way down here and write in the following. So 0, 0, 2 and 3. There we go. So this pattern would continue. And this would represent that very original graph we might sketch out here. But of course, it's going to be reflected about the x-intercept, which in this situation, I can actually just flip all of these negative points and make them as -1 and 1. I can make it as -2 and 2, -3 and 3, -4 and 4, and then I'm going to sketch it out that way because I'm trying to represent the absolute value of just x, which is considered to be the original function. So let's write this as y is equal to the absolute of the x. Perfect. Okay, now we're going to do transformations to all these points. Starting off with the origin, we know that the new origin point is -2 and -4, which by the transformation puts it right here. In terms of the other points, what we can do is we can just take them one by one and put them into this function. Let's say I choose this point here, 1 and 1. Well, 1 minus 2 is going to be -1, so I go to -1 for that point. And then if I put in 1 for y, 3 times 1 is going to be 3. 3 minus 4 is -1. So my new point would then shift to here. Okay, let's do the same thing. If I go and I take 2 and 2 and I plug it in, which is this point on the original. 2 minus 2 is 0, so now we shift down to 0. If I take 2 times 3, which is 2 times the y value, is 6. 6 minus 4 is +2. That means that my y value is +2. My x value is going to be 0. So that means that it now crosses here instead. Okay, now let's just do one of the left points, and then by symmetry, I think we can figure this out. Let's say I choose -1 and 1. -1 minus 2 is -3, so it puts me over here. For my y value, 1 times 3 is 3, minus 4 is -1, which puts me to here. Therefore, my new point's here. And then by symmetry, we can pretty much sketch out the rest. At -4, we're going to be at +2. And now we can connect this with a dotted line just to differentiate it a little bit in case you have like pencil or something like that and you can't differentiate any other way. I'm going to write it like this. I'm then going to draw my dotted line like this going through here. And then we're going to indicate this as y is equal to the vertical stretch of 2, absolute of x plus 2, and then -4. This is that new graph. Now, something I want you to notice, do you see how it went from a wide graph to a more steep graph? Or it was a little bit more flat and it went to something a little more vertical? That's because our vertical stretch factor is greater than 1 and it's some sort of whole integer value. When you see that, it condenses the graphs. And then not only that, but now we're able to form this new graph here. Now, should we state the domain and range? Sure, why not? I think that might be something to add to this. I wasn't asked for, but maybe we do it. So I'm going to state the domain. And do we want to do, maybe even we just add to this and we state the piecewise function here. So my piecewise function is going to be the following. We have y is equal to, we take 3 absolute of x plus 2, and then -4. This is going to be the following. We take this and separate it into, for the first one, we're going to have it as the positive variant, so x plus 4, or x plus 2, sorry, -4. And this occurs when we have it all to the right-hand side. And it's going to be the right-hand side of this P and Q. Maybe I should even put that on the graph here. The P and the Q, or the lowest point here, is at -2 and -4. There we go. So this occurs when we have the positive sloping line when it occurs to the right-hand side of this. So when x is greater than or equal to 2. For the other one, we have it where it is negative of all of this, x plus 2 -4. And then this one is going to be where x is less than the -2. And this one should have a -2 as well. Awesome. Okay, domain and range, let's just fill that in here. So right below here, domain, no surprise here, x such that x is an element of the reals. Our range, well, because there's been some transformations, we now say y, where y is greater than or equal to our lowest value, in this case, which is -4. And once it's past -4, it can be any real number in the real plane. Y is an element of the reals. Done. Awesome. And then sometimes, again, what I like to do is I like to put this part here right in the middle here, because it's defined as these two coming together. All right, so now in this next one, we're going to sketch out the absolute value here. And we're going to sketch out the original just like we did before, and then sketch this out based on the transformations. And then if we have space, we may throw in our piecewise and then throw in our domain and range, but we'll see what we got. So starting off with writing this in terms of its transformations, we got to rework this a little bit. It's going to be y is equal to, we have the absolute of -2x minus 8 minus 3, right? Now, we don't like it in this form because this actually doesn't tell us about the horizontal translation. When we have some sort of thing attached to the x, what we want to do, even back in quadratic functions, is we want to factor this out. And this applies even to the 30 level of math. What we're going to do is we're going to take out a factor of -2, which we have to keep the absolutes attached to it because the absolutes are being applied to it. We're going to write this as multiplied to. On the inside, that after we take out the -2, we end up having x minus 4 absolute minus 3. Now, this leaves us with the following. Y is equal to the absolute of 2, which is 2, times x minus 4 minus 3. Perfect. Okay, now we have our function in a better format where the absolute value doesn't have some sort of coefficient attached to it in terms of its x value, and now we can accurately describe the horizontal translation, the vertical translation, and the vertical stretch factor. And again, if you pull anything outside the absolute still applies to that number. Okay, now let's describe our mapping notation. We have our x and y, which describe this as the following. Our x's are actually adding 4, our y's are going to be 2 times the y's and minus 3, which is the p-value. Remember, with the p-value, we don't change the operation. So I know with the p-value, we change it. The q-value, we don't. Just make sure you're still following through on that. In terms of a vertex point, or our new lowest point, which we're going to call our p and q, that occurs when x equals 4, when y equals -3, which is our p and q. Okay, from here, let's sketch out our original graph again, or our original y equals the absolute of x. So we have 1 and 1, 2 and 2, 3 and 3. We have -1, 0, 0. We have -2 and 2, -3 and 3. Now we're going to sketch our line through this. Put arrows on the end. And then we're just going to make sure we indicate that this is what that graph is. So it's going to be our y equals the absolute of x. Now from here, we're going to plot out our vertex point, which is 4, -3 for our new graph. So it actually puts us somewhere off to the side. And I want to make sure that we got this right. Oh, that's why. I was going to say, I was like, this graph doesn't seem like it's going to fit what we're looking for. We have to actually go back here and make sure that this changes to a positive, and a negative here, which makes this negative. So let's just go back in and edit this here. Because when we factor out a -2, this ends up becoming a positive instead of a negative, positive instead of a negative, which means we actually subtract all x's by 4, and meaning that our p-value is actually -4. That makes a lot more sense. So we go to -4, -3, which puts us to here. And I want to show this in red, so I'm going to backpedal that just a slight bit. There it is. Now what we're going to do is we're going to take all the right points here on our original and then just do our transformations according to the mapping notation. If I take x equals 1, well, 1 minus 4 is -3, so our new point will occur at -3. And then in terms of the y value, 1 times 2 is 2, 2 minus 3 is -1, it puts us to here. Now, by symmetry, we can also put the point that is to the left. Okay, let's do our next point, which is for the right-hand side here. Here it is. If I use x equals 2, 2 minus 4 is -2. If I plug in 2 for y, 2 times 2 is 4, 4 minus 3 is 1. That means that my point that's on the right-hand side here is going to be at -2 and 1, which means my other point on the other side is going to be at -6 and 1. And therefore, now I have my absolute value function as a sketch here. I'm just going to put dotted line, dotted line, dotted line, connect them through. Perfect. And then again, we're just going to indicate that this is our y is equal to the 2x plus 4 and then minus 3. Excellent. Now, again, what you notice is that because the vertical stretch factor is 2, which is in comparison to the original, which is 1, we see that the graph kind of gets a little bit more narrow or is a little more condensed. And then again, we want to make sure we indicate our vertex point, which is down here. It's at -4 and, sorry, -3. And -4 and -3, yeah, perfect. Okay, just making sure we got the right values in here. -4 and -3. There we go. So now if we were to state our piecewise function, which it doesn't look like we have room for here, I mean, we could try to force this. Yeah, what we're going to do is we're going to move all of this over here as far as we can left, and then we'll be able to fit all this information in here. So let's say we write the piecewise. Well, the piecewise is a definition of the following. It's our y, which is equal to 2x plus 4 minus 3, which is equal to the following combinations. This might actually be too close in together. I don't think we'll be able to do it for this example. So I'm just gonna leave it without it there. Unless maybe I can do this at the bottom. Yeah, let's try and fit this at the bottom here. So I'm just gonna move this back here where it originally was placed, right here. I'm just gonna move it up a tad. And then make sure it's not too close to the text. And then we're just going to put this right at the bottom. So our piecewise would be defined as y is equal to, we have 2 times the absolute of x plus 4 minus 3, which can be defined by the following combination. The first one is the positive case, so it's 2, and then instead of the absolutes, we are at brackets, x plus 4 minus 3. And this is for all x values that were greater than the vertex value of x, which is going to be our x is greater than or equal to -4. Our negative case, or -2 times x plus 4 minus 3, occurred when x was less than -4, or to the left of -4. The only thing we won't be able to put here is our domain and range, but I mean, I trust you can do that. I'm not too worried about that. And again, what I sometimes like to do with this is I like to keep the function here right in the middle, because in math texts or more formalized math texts, they like to put it right in the middle of that piecewise there, where our kind of our bracket, our middle section is right along the equals. Okay, now for this situation here, if the a value is negative, then the graph opens downwards. Of course, right? This is when we talked about vertical stretch factor. If the vertical stretch factor had a negative, it actually caused all the values to flip over the x-axis, which it was no surprise to us and maybe just requires a little bit of review, but we know that from here. Now, in this situation below, what they want us to do is they say, write the equation of the absolute function in the piecewise notation or piecewise function notation for each of the graphs below. So there's a couple things we need to know right away, and it's dealing with our vertical stretch factor. Once we know our vertical stretch factor, we also know the point that it flips across, or its vertex point. We then can figure out what this graph is. So on this graph below, I want you to annotate a couple things here. Our P and our Q, which is our lowest point or our vertex for this situation, is at -2 and 0. We also have a point over here which is at 2 and +1. Now, if we describe the slope between any two of these points, which is our vertical stretch factor technically, our vertical stretch factor is going to be where we do our rise over run, and let's annotate that below here. From left to right, we go up by 1 unit, we go over by 4 units. That means that the vertical stretch factor, or the a value, is going to be 1/4. So if we have this 1/4, and maybe I can even put this as like a dotted kind of segment here. So dotted, 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 there we go. We go up by our 1 unit, and we go over by 4 units, giving us our m equals 1/4. What I'm going to do is, if I know my vertex, I know my slope, I can actually put this all together in the following way. Therefore, as a piecewise function, our original piecewise is equal to, we have the following segments. So it's going to be 1/4, absolute, x, and if it was -2, it's going to actually be +2 for our p-value. Our q value was 0. We can put the q value if we wanted to as 0, but I don't think it's going to be worth it. This is equal to, as the piecewise, 1/4. We have our x plus 2. And this positive sloping line, or the part that was on the right-hand side, occurred when it was greater than the x-intercept, which is 2. So we write x is greater than or equal to -2. Our other component was the negative variant of this. We put negative, and then we write all of the exact same terms here, x plus 2, and this occurred when it was less than -2. Okay. And again, why do we write this equals here? I know that this can fly over our heads. Like, why wasn't the equals on this one? Why was it here? It's because if I drop the absolute value bars and I made this round brackets like we did in our piecewise, then the original function would actually have a positive sloping line, meaning the original graph or the original linear line looks like this, and it overlaps all of these values on the right-hand side. So we always associate the equals with that graph there. And I'm just going to pull all this over. If you've already copied it in your notes, all good, but I'm just going to center it a little bit just so it's a little better for us. Okay, let's do this with our example down here. So let's say I go to my vertex point, which is going to be at 5 and what looks to be 1. Let's make sure we copy that in here. So 1 for x and 5 for y. Okay, now we have a couple points here, or one point in particular. We have this point at the y-intercept, which is 0 and 3. Okay, what is the slope between these? Well, the slope that's included on this is equal to go between these 2 points, I have to go down by 2 over by 1, which means that if I go down by 2 over by 1, it's negative 2 over 1, which is just simply equal to negative 2. So we have a slope of negative 2, and again, we could write this in a slightly neater way here. So maybe I take this, I bring this over here. I'm going to write in my slope where we go over by the 1 unit, down by the 2 units, down by 2, over by 1. Our slope is negative 2. On the other side, if we were to describe it this way, let's say we go on this side of it. Well, to get between the 2 points here, we would still go down by 2 and over by 1 in this situation. And I should actually read this left to right. This should be a positive 2, right? Because it's a positive sloping line. So to go from those 2 points, we have to go up 2 over 1. To get on the other side, though, we have to go to the left by, or to the right by 1, and then down by 2 units. So this should give us the positive slope here, or sorry, the negative slope, 1 and negative 2. There we go. That looks better. And the reason I'm doing this point here is because it's by symmetry. If I have this point by symmetry, it is at 2 and 3. And we get the slope reading it left to right. Now, if we know that the slope is negative on this on the left hand or right hand side and positive on the left, I keep confusing those for no reason. We can write out our piecewise using the fact that we have our P and our Q, and we also have the given slopes here. Therefore, y, which is equal to the slope, which is in this case our, and we want to consider it of what would be for the potential first one here. If it's downwards facing, that means that, like, and what I mean by that is if the absolute faces downwards like this, it means that the original stretch factor was negative, meaning our left hand, or right hand side one, sorry, not the left hand, but the right hand side determines this overall slope. It's negative 2 absolute of x minus 1, because it was actually at positive 1, we make it negative. This is going to be positive 5 for the y values, or for the q value, because we consider our p and our q to be at positive 1 and positive 5, but again, we put it in here and it makes it negative. Now, we define this using the absolute of the following. This is equal to, we put our big bracket, and now what I'm going to do is write the original, which was negative 2 x minus 1 plus 5. All of the negative sloping line occurred when we were on the right-hand side of this p-value. So we're going to write where this is to where it's greater than or equal to 1. And then the negative variant, or negative 2x minus 1 plus 5, occurred when it was all to the left of that 1. And this would be the piecewise that describes it. Now, again, just a big difference here. If you see that the V shape that's formed with the linear lines here faces upwards, if it faces upwards, it means the original graph had a positive slope, and it was this line here, which created the common values that would be at the greater than or equal to 2 for the linear line. If we have it where it faced down, our A value is negative. The A value being negative means that our original function that we're going to describe here has a negative in it. And so all of that occurred when it was on the right-hand side here, or where the line would make a negative slope. All right, here's where you're going to want to go to your assignment. This is a lot of technical information. So if some of this kind of went over your head a little bit, no problem. It's going to require practice. It's going to require review. So go to the textbook, apply some practice problems, and then make sure you sketch these out accurately on a graph. All right, good luck with your practice.